Well, this is John Black, Super Chemist. This is part 5, wave particle duality, and the double slit experiment. Boom! Okay? If I have a baseball and I have to throw it through a little tiny slit like this, a little hole like that, when the baseball can barely get through it, and I'm like 40 feet away and I gotta throw it? No. First of all, most of them ain't even gonna go into the hole, okay? Second of all, the ones that do get into the hole, look at this. You have like 50% probability of, hitting one of the sides. And if I hit one of the sides, which I'm going to most likely do, it's not just going to go through there like swish when I'm throwing 100 baseballs. No, that's not going to happen. And what happens when you graze it, it deflects off a little bit. But what happens when you hit it and you know what I mean, the best you can hit it, where it flings off to the other side? Yeah. And you hit it in between those two things that I mentioned? Yeah, then instead of it getting flinged over, and instead of it just being slightly nudged over, it's going to be in somewhere in between. Yeah. Guess what? It's going to look like this. It's going to look like a freaking interference, pattern, right? And think about it. Seriously, think about it. Do you think that if you threw baseballs with this slit, right, that you really think that you and if you're like a professional baseball player, then you don't count. I'm talking about, someone normal, right? Or average or whatever, you know what I mean? You really think that's going to happen? I don't think so. They're not going to swish it through this hole, okay? It's going to hit the sides all the time, probably more than it don't hit the side. It's going to be flung off into these whatevers. And then if it's baseball, yeah, it can kind of get flung off in all different ways, right? And so he'd fill in this whole pattern, right? But I want you to think about it, though, right? If the ball vibrated, and it was a wave, right? When it comes into this thing, right, it has this whole wavy thing that it can bounce off of. You know what I mean? And as it's moving, it's going up and down, or it's going back and forth, right? Whichever way it's going, or whatever. Actually, it has to go. It's going up and down like this in the direction it moves. Okay. So if this ball was moving up and down, that means it's moving that way. So if the ball's going into here, it would be going up and down as it's going in. You know what I mean? It has to be up and down in the direction he's moving. But my whole thing is, though, you're going to be hitting this thing. The wave function, why does it make this interference pattern? Because it's interfering with the freaking slit sides, you idiots. Oh my God. And why does it do a diffraction thing even though it's not a wave? Because it's jumping up and down, and when he hits the sides, it's going to hit it using, the probability is going to be from a wave equation, obviously, if you're moving as a wave. So this is the first two lies. They say that this baseball, they say, look, an electron has to be a wave, right? It's not a particle, because we believe in magic. And you know why? Because when you throw this baseball, through these two slits, you make this kind of pattern, where you get two patches. Okay, first of all, that's a lie. No one can throw the ball through these slits and do that, okay? That's insane. You'd have to be like standing right in front of the slits, all right? You would make this, okay, because of all the deflections or whatever. But this doesn't vibrate, see? And an electron vibrates. They all know it vibrates, okay? And yes, the baseball vibrates too. But it's so big that its vibration, you can't see, it doesn't do anything. Who cares? Okay? The electron, it's gone. Okay, it's vibrating. It counts. Right? So that's so disingenuous, because every physicist on this planet, well, not all, but 95% of them all agree that this electron is vibrating, and there's 0 point energy that is making it, it's reacting with space-time, man. And I guarantee you, if you put a thing in that baseball, right, and you made it vibrate you know, just like this. I have the sine wave up here, going back and forth, and then you got a whole bunch of guns, and you know, so you can make a pattern like this, you know, like this laser, right? And go and make all the balls hit there, right? While they're vibrating, I guarantee you, you'll get a diffraction. You'll get a interference pattern that you would make, okay? And even without the ball vibrating, that's still stay. You're going to end up with this thing here, an interference thing, because the sides of the thing are going to interfere with you getting a swoosh. You're not going to, it's not basketball where you're swoosh and it's just going to swoosh right through there and not touch the sides, okay? We live in the world, okay? That doesn't happen, all right? You're going to be hitting the sides all the time. That's why, that was the whole point of making the slits that thin and skinny. You want it to be smaller than the wavelength of the freaking thing. Why do you think they do that? So that you can hit the sides, okay? And you can get interference. Yeah, so this interference is scattering, diffraction. Yeah, it's not that it's interfering with itself, okay? It's interfering with this little tiny hole that you admit is as tiny as the wavelength, right? Then you admit that everything, the photons vibrating, the baseballs vibrating, everything's vibrating, and you're trying to throw it through a little tiny slit that's so small that you have more chance of hitting the sides than you going through straight and not hitting the sides. And you're telling me that you don't understand why you get, you know, your balls and your things are going all over the place, like it making an interference pattern. Really? You don't know why? I think all these people, all these physicists, we should force them to go to my house. Now get some slits like this, give them some baseballs, and let them prove that they can throw it right through the slits. Swish, swish, never touching the sides, because that's how life works, right? That's how physics works, right? Things go through a slit that's so tiny that you can barely get through it, but you're never affected by the sides. No. You have to have magic where you're going through both slits at the same time and interfering with your own self. That all makes sense. Better than saying, hey, the electron, it vibrates. The light photon, it vibrates, and it's going through a tiny slit. So it's hitting the sides and interfering and getting bounced over here and bounced over there, making an interference. No, you wouldn't want to say that. It makes more sense. It sounds so much more sane to say, hey, you know what? You go through both slits, and then you interfere with yourself. Because that all makes sense, and it's not insane at all. So, and the other thing that they did ingenious, you know, not just, because this doesn't vibrate, right? This does not, I mean, it does vibrate, everything vibrates, but it vibrates so little that who cares? Doesn't, whatever. You cannot compare this to an electron. You can't say, well, we know an electron's a wave because if it was a particle, it would act like a ball and make these two lumps here. Okay, that's so, especially when, I could see if it was like, you know, controversial or something, but everybody says that everything vibrates, right? The electron's vibrating, you know. So if they know it's vibrating and they know the baseball isn't vibrating, you know, it's not vibrating to do anything because it's so small, why would you compare it? Why would you use that as an excuse? So I don't even think this, you know, diffraction, scattering, and interference. No, you know, yeah, it is scattering. It's scattering off the sides. Yeah, there is interference. The sides are interfering. Yeah, it is diffracting. Yeah. So when it hits off of that, it gets diffracted. Yeah, it's just one way or the other. You know what I'm saying? Right? Now, I know if you are an adult or even a young child, we've all experienced this, what I'm going to talk about here. Here's this guy, he's playing ping pong, right? I didn't draw his path very good. I wanted it to be a lob, you know what I mean? This guy lobs it up, comes down, and you'd think it would bounce off it this way, you know, because it came like that, but it doesn't. It goes off of a tangent, like off out of nowhere. It's like, it makes no sense, right? You know, yeah, we've all seen this, right? Where you throw something and it hits the corner, and you think it would go this way, but it doesn't. It goes the other way. The ball is not a wave, okay? This ball is not a wave. It's not a wave, okay? It's the ball is a particle that experienced scattering. You know what I mean? Interference by this table. This table interfered with its path and scattered it, okay? It's not magic, right? This thing that, you can't be scattered or have interference or diffraction and blah, blah, blah if you're a particle. Well, what? Bull, okay, first of all. Second of all, look at this pendulum, right? It's a clock. Pendulum oscillating back and forth, right? Ring, 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 ring. Yeah, it's not a wave, okay? We can describe this clock, right, this pendulum. We can describe it as accurate, as actually more accurate, okay, with a wave equation, okay, then you can describe quantum physics with a wave equation. Yeah, does that make this a wave? Does it make it a wave? No, it doesn't, okay? How about the spring with the mass on it? Pull it down, right? Oscillates, just like this was oscillating. The math that describes this is a wave function, okay? Does this make this a wave? No, it doesn't make it a wave, okay? How about this rotating thing, this spinning thing, this orbiting thing, right? Yeah, we use wave equations, right? Wave equations to describe everything about that. Everything about oscillation, rotation, spinning, springs getting whatever, pendulums, all of it, okay? They're not waves just because you can, just because their path is described by a wave equation. The wave equation, okay, it doesn't describe the object, okay? It describes the path, all right? See, they did this thing right here, okay? They're doing the same mistake with the Stern-Dirac machine and with acceleration, right? Here's a spaceship, a blue spaceship and a red spaceship. They're millions of miles apart. They don't know nothing about each other, right? They're floating through space. They don't have no rockets or nothing, right? Constant velocity, right? They're all floating, okay? They're unaware of the other people, okay? You can see I put their path right here, right? They're going to intersect sooner or later. We would all say that these guys, they got no rockets. They're in the middle of space. They're all floating. We can all admit and say that they are in an inertial frame, right? But I took the middle part here. You can see the angles are both equal. And I divided it up into 3 units of time. You can see the first unit of time, he moved this much close to there. The second unit of time, look, it's more. He moved more. And the third unit of time, even more. That's what acceleration is. You're moving, you're going faster and faster towards your whatever, right? But you can plainly see, okay, these people are a million miles apart, and when they intersect, it's going to be a million miles from now, 100 million years from now, okay? They're obviously still floating, they're in an inertial frame, but what does everyone say? Oh, I don't understand, man. They're being accelerated towards each other. They're in an accelerated frame of reference. This is how Earth is, right? This is Earth, and this is you falling, right? You're not accelerating. Space-time is being accelerated down. You just float there, staying, floating there relative to space-time. So if space-time is going, and you're also accelerating down, yeah, your path is accelerated, but you yourself, you don't feel any force. It's the same thing here. We're doing the same exact thing. Okay? The path is accelerating, not these people. They're still floating, you morons. Same way here. The wave function does not represent the particle. It represents the path. I don't understand why it's so hard to just say, hey, the particle is a particle, but it vibrates, and because it vibrates, it acts like a wave, and all the math, you can use wave equations to describe its path and its trajectory and probabilities of where he'll be, but you do the same. We do the same thing with pendulums. We do the same thing with springs, rotating things, orbiting things, spinny things. But we don't go around saying, hey, that basketball that was spinning, hey, that's really a wave, man. You can't tell it's a wave? Oh, yeah. That pendulum, yeah, it's a wave, man. Yeah. Because our math tells us it's a wave. Everything, this thing does everything our wave equation says. It has to be a wave. Like everything in the world